All right, welcome everyone to today's A16Z Crypto Research Seminar. Very pleased to introduce Ittai Abraham. Ittai's been working in the intersection of distributed computing, cryptography, and game theory since way before it was cool, even maybe before blockchain protocols even existed, I would say. So he's obviously perfectly positioned to do lots of great research in the blockchain area, which is what he's done over the past decade plus. And today he'll talk us about mental models for TEEs.
Thank you, Tim, for inviting me, and thank you everyone for coming for my talk. Very excited to spend time here and work with such a strong team of researchers, interns, and visitors. In particular, this is a great opportunity for me to actually work in person with Karthik and Ling, something that I haven't done since 2016. So, yeah, very exciting. Okay, so I'll talk to you today about trusted execution environments. And there's not going to be a lot of math, so don't worry. It's going to be more of a kind of overview of this topic, and I hope you'll get something that you want from. So I'm going to talk about multiple different topics, a little bit about kind of in general how I view security and the friction around that. We'll talk about cryptography and the real world or the physical world, and then kind of go into these trusted execution environments. And at the very least, I want to talk about how they relate to consensus, how they relate to integrity proofs, and how they relate to this notion of accountable privacy that I'll be talking about. Okay. So let's talk about kind of this notion of security versus friction, which I find in many of the dilemmas that I look at in the real world is kind of a driving trade-off. So in some sense, you ask yourself, why do we want security? So if you're more of a Bayesian thinker, it's because you're kind of risk averse and you want to reduce the probability of having bad events, maybe reduce your variance. Or if you're kind of worried about the worst case, then you kind of want to prepare for the worst case. And really the question is, kind of at what cost? And sometimes there's this kind of inherent trade-off, right? If you spend a lot of effort trying to protect yourself, then at some point it becomes too costly. So you really want to find something that makes sense in terms of this trade-off between security and friction. And so at least for me, traditionally, most systems kind of don't go for this kind of high security trade-off. They usually provide relatively low security because they want to basically get as low friction that they can, because high friction is kind of stopping usually value created. And at least in some places, this kind of creates an illusion of security, and in some cases even kind of not a real value for users. And at least to me, kind of one of the biggest disruptions in this trade-off is this appearance of Bitcoin, which is kind of one of the extreme examples of something that provides very high security and also provides relatively high friction. It's there's multiple reasons why it's not easy to use or to maintain and so on. And maybe the next kind of evolution for that is these blockchain disruption, which is kind of more generally trying to get at a point where it still provides high security, but kind of lower friction. I would say global computer, right? So this is kind of the high level goal of this whole topic. And I would say the overarching goal in this space is to kind of get high security but get low friction, because we know that anything that has high friction or even medium friction will just not be adopted and used. And so this is really the kind of important trade-off. And I personally think that one of the ways we're going to get through this is through a kind of major disruption that's happening upon us. And so what will be the way to kind of get high security and low friction? Yeah, so I actually think this AI is going to make a huge difference here. So this is one of my big predictions, that these dramatic productivity gains that we're seeing will actually be translated to the ability to dramatically reduce friction. So we're already seeing this by basically being able to build way more complicated systems. But I believe that over time we'll actually be able to get even better reductions in friction, and that will allow us new points in the trade-off. So things that we didn't believe were feasible or efficient will actually now become much more efficient. And I'll talk a little bit about that. But I want to focus kind of today on cryptography and hardware. And I'll kind of ask you this kind of question. We all believe in cryptography, so do we need to trust the physical world? Is there any hardware that we need to trust if we kind of just have cryptography and cryptography works and is wonderful? So anybody think we don't need any secure hardware?
So what's the question? Do we need secure hardware or not?
Yeah.
It depends on the application, right?
Yeah, good, great, yeah. So what application you don't need anything?
Sorry, what's the question?
Yeah, so I think Elaine's answer is actually quite good. So what I want to say is that for many things that we take for granted, we'll see that we do need some sort of secure hardware. But for others, for example, let's say the fact that we can use hash functions and we believe that they're unbreakable, right? I don't think we need a secure hardware for doing that. I mean, so here's the thought experiment that I want to kind of go over. I want you to kind of think about a world where there's what I'll call no physical security. So in that sense, the adversary can always kind of reach into any secret that you have, right? If you have a USB key that has a secret, it can reach and look at it. If you have a secret note with your passphrase or password or whatever, it can look at that, right? So this is kind of a very daunting world where basically there's no physical way to kind of isolate and keep a secret. And I guess my point is that this kind of world is very hard. Like there's nothing we can do in this world. So as Elaine kind of observed, there are things that you can do, right? So for example, you can do some sort of integrity proofs, right? So there's a little bit you can do. And maybe even, if you assume that there's some randomness, then maybe the adversary can't predict randomness, and so you can do randomized algorithms. So there's a little bit of things you can do, and some, area of cryptography, but kind of most of the things that you would like to do, public key cryptography, having secrets, being able to sign, being able to encrypt in such a way that some people can decrypt but others cannot, all these things be kind of impossible. So I guess my point here is that whenever we think about cryptography as kind of solving all our problems, we're actually assuming some root of trust of physical assumptions. There's essentially, you cannot do anything, or there's very, very little you can do with cryptography without having any physical trust. Okay, so that's kind of the main point here, and yeah, that's kind of the essence is that you want to, or if you don't have a way to guarantee that there are secrets that will not leak, that the adversary cannot look at, then there's very little we can do, right? If you want to maintain assets, if you want to have some cryptocurrency or any sort of access to your bank and so on, then you need to have some sort of secrets, some sort of biometric secrets, some sort of passphrases, some sort of digital secrets that cannot be accessed by others, right? If that is not the case, then I don't know what to do. And so I guess the thesis here is that if we already have to trust hardware, then I guess the question is, why should we trust it, or which hardware should we trust? And the other thing that I'm going to try to ask is, okay, if we need to trust hardware a little bit, then maybe why not should we use that little bit of trust to actually build hardware that we trust it even more, to allow it to do more things than just, say, keep our secrets. And in particular, there's kind of this meta question that if we have time, we'll go over at the end, which is, what is the minimal trusted hardware that we would need? And how would we even guarantee that it is trusted, right? Maybe today you buy a secure wallet or a ledger or something that you can kind of keep your cryptocurrency. So how do you trust that thing is actually doing that and doesn't have some sort of backdoor, for example? Okay, so I guess the main thing I want to kind of convey here is that in a sense you can think of cryptography as a reduction, as a way of taking a small amount of physical trust and using cryptography to create a lot of trust. Yes.
Can I ask? I have a question about the TCB. So I wonder, does Intel believe that TDX is more secure than SGX?
That's
because I think the trust model is different.
I'll talk about TDX at the end, and I'm not representing Intel in terms of their beliefs, but I will discuss that. Thank you. Yeah. I want to go into trying to define so formally how we can talk about physical trust. So we have something that we believe is physically, we can trust it physically, and so what does that mean? So we want to kind of define an adversary and say, hey, this type of adversary cannot access this type of physical machine. And so for that, I want to kind of separate different types of adversaries. So I'm going to go through this hierarchy. Maybe the easiest one is a remote adversary or a network adversary. So again, imagine this is like somebody who can access your laptop or your phone remotely, right? Which is kind of what may happen once your machine is connected to the internet. The other is maybe it's running local software. So maybe if you're keeping secrets on your laptop, then maybe there's another application running on your laptop. Or maybe if you have a USB device, but you connect it to your laptop or your phone, then then something can run on your phone and so on. So that would be kind of a software adversary. It's still an adversary that can only just run software, but it's running close to this secure hardware. And the third thing is kind of physical adversary. So this is the adversary where you give it your secure hardware, and they go to their lab, and they have all the lasers and things that they need, and all the measurements to kind of try to figure out what to do. And there are going to be different types of technologies, and in different ones, we'll see we get different type of guarantees against these different types of adversaries. So this is kind of, I guess I won't say the beginning, but the beginning that I want to start with what are these secure hardware entities, and this is kind of a TPM. This is a chip, a piece of hardware. Sometimes it's actually virtualized, so it's not necessarily a piece of hardware. But the idea of this piece of hardware is that it can kind of do these three things. It can store secrets inside of it. So in that sense, it can keep secrets that people from the outside cannot see. It has a monotonic counter, by the way. So for the consensus people here, that kind of allows you to do all these fun things. But I'm not going to talk a lot about that. And the third thing which is interesting about these systems is that we believe that they can trustedly measure other parts of the system. So in particular, for example, if I want to see what's running on my CPU, I believe that these TPMs have a hardware trusted way of looking at that and measuring that. So measuring kind of will be the noun that we're going to use for saying I'm kind of looking at what is running on a CPU. And again, if any one of these things break, right, then it's going to be hard to use these things, right? So even if I trust it, if it's kind of looking externally and reading things that don't exist, then it doesn't help me. Or if I trust it, but it leaks its secrets, it doesn't help me, right? Or if you depend on this monotonic counter and it's not really monotonic, then also kind of horrible things happen. Yes?
First two assumptions make a lot of sense to me, but why is the last one a reasonable assumption?
Oh, this is physical trust of hardware. This is how it's how it's built. I mean, I would say you think this is reasonable. So it really depends on your attack model, right? Like, but I would say I'm saying it differently. I'm saying you need these three things in order to make it. You need to trust these three things. Whether it's whether you believe it is trusted or not is kind of make sense?
Why do you think it's not reasonable?
Can measure other parts. You mean you can measure what's in the memory?
Yeah, in particular,
memory
there's.
I can design a malicious
Yes.
RAM. When you
Yes.
try to measure, I give
Yes.
you a different set of
Yeah.
bits.
So definitely you have to assume that there's more to the design of the system than just the TPM, but also kind of the thing that it can measure. It can measure in a trusted way. Absolutely. I mean, I think that's part of the mental model that you should have, right? So I'm glad that you, yeah.
This might be a silly question, but it feels like there should be something more here because, like, for these three conditions, isn't the human mind trusted hardware? Like
Yes,
if
yes.
Keep a secret, I can count, and I can see things,
Yeah,
and if you need to trust me, but there's some laws saying I'm not allowed to do things.
That's a very good observation, and I would say, humans also have this property. And I think against a physical adversary with a wrench, you could argue whether you have this property or not. So it really depends on the physical adversary. But for a software adversary, somebody just talking to you, you could also imagine some risk, right? But you're absolutely right. Like you should think about this is a good mental model, not just for TPMs, for any type of secure hardware. Let's say a piece of paper that has so on, right? Yeah. Okay, so kind of this is what TPMs are. And by the way, all your servers and laptops have these things, and I'll talk a little bit more about this. But anyways, what is good at this is that basically this allows you this notion of an attestation. So basically, what is an attestation? It's basically taking the first thing and the third thing together, right? So I'm measuring something in the external world, and then I use the secret that I have to sign it. Okay, and then basically by having a signing of a measurement, this is kind of what can be called an attestation. And I can even do something more sophisticated, which is I can keep secrets. And I can release these secrets only if this signed measurement matches a previous signed measurement. This basically allows me to kind of put a secret into a very specific piece of code and then make sure that the same piece of code is running again. I can kind of I can release the secret just for this type of code. There's a monotonic counter here. There's like this nice literature from the 90s and 200s about BFT systems with monotonic counters. I'm not going to talk about it a lot for many reasons. This is not very efficient, and let's just put it there and not talk too much about monotonic counters, even though I like them a lot. In terms of the security model, so I would say definitely people believe that TPMs are secure against a network adversary, and even a software adversary, again, even though there were challenges, there are virtual TPMs that are implemented in firmware onto larger coprocessors, and there might be risks there as well. And in terms of physical security, people say it has a relatively good physical security. So I'm not an expert in these things, but my guess here is that there are maybe agencies or groups that, if they have physical access, can spend effort to actually break into these things physically. So let's say differently. Nobody's claiming that this is physically unbreakable, at least not that I know of. And okay, that's kind of one problem. The other problem is that obviously these things need to be upgraded and updated. That's another story, which I won't go into too much. But I will tell you kind of what really went wrong with this type of paradigm. So the paradigm basically was that you have this small coprocessor that you really trust, and then you basically load the bias, and the TPM would measure the bias and kind of sign it, and then check that this is the right bias, and then load the operating system and measure that, and then load the application. So you kind of get a sequence of trusted boot. And basically this trusted boot would be kind of verified from the BIOS to the operating system to your applications. And typically the problem is that what the TPM would end up verifying is, in a ZK language, a huge, enormous circuit, right, of all the applications running on your machine. And so if you're kind of, yes, you verify that that is what's running, but that huge thing might have so many problems in it. So this is this kind of large TCB problem. Trusted compute base, right? This is the thing that I need to trust, right? So I think that's kind of what somewhat failed with this paradigm. And what this kind of led to is systems that don't kind of verify your whole system, but to verify smaller parts of it. So for example, your phones have kind of something similar to a TPM. Wallets definitely have that. And HSMs are kind of dedicated servers that are kind of focused on minimal functionality just for managing secrets.
I think you can use TPM to verify only the piece of code you care about, but it's not fast. I think it's inefficient. But it's not necessary that you have to verify.
I'm not sure the problem is inefficiency. I would say the problem is that usually like a platform runs a lot of code. And I mean, if you wanted to, this goes back to the security versus friction. So you could have a very, very dedicated system that just does one thing. That's essentially kind of what an HSM is. But this is maybe going to be in the next slide, which is kind of the way compute evolved is by basically packing a lot of work into one server. And so once you pack a lot of work into one server, then, okay, you can verify that a lot of things are running on this server, right? But it's not clear that that gives you a lot of security value.
But what I'm saying is like there are works that showed how to use TPM to verify only a small piece of code that you care about. I think I have a paper called Bind, and then Brian Panel has a bunch of papers on that topic.
Great, yeah.
So it's just like when you do that, you have to go through a heavy context switch.
Yes. Yeah, that's a great comment. Yeah, that's a good point. So you can use this. I'm not saying you cannot. Yeah, that's a really good comment. Thank you. Okay, so I want to say that the next thing that happened is kind of this, the cloud computing kind of got important. And really kind of this virtualization allows you to pack many, many virtual machines into kind of one physical machine. And this kind of gives you a lot of elasticity and essentially reduces the friction, right? And so by reducing the friction, the cost of running things, you get a lot of economic value here. And by running these things at scale, you get also a lot of value. So anyway, this kind of made a very reasonable economic sense, but then kind of brought in a new security problem, which is kind of this outsourcing of computation, right? And so this is kind of a new security problem, which kind of has two fundamental problems. So it used to be that I ran stuff in my data center or on my desktop, and I trusted it more because it was my hardware. I had physical security there. Now I'm kind of outsourcing it to a cloud, and this kind of brings me a new problem of outsourcing. And there's two things I want to worry about. One is if I'm outsourcing computation, maybe it's not doing what I told it to do. Maybe it's doing something else. That's kind of the integrity problem. And the other problem is kind of a privacy problem, right? Maybe it's doing what I'm telling it to do, but it's looking at the input or even looking just at the code that's being run. Okay, so these are two kind of natural problems. Make sense? Okay, so I would say the next evolution here is kind of this notion of a trusted execution environment, which are basically came trying to address this problem of cloud compute, gain the economic efficiencies, but give you some sort of security okay, and the kind of high-level ideas just do two things, right? So previously we kind of ran a machine, one machine on our hardware. Now we're running virtual machines, right? But you can just think about a machine. We're just running them virtualized, running a lot of virtual machines on one piece of hardware. Basically, what we want to do is we want to have for each of these virtual machines a separate TPM. So we already know what that means. And so that kind of will give us integrity that is more granular. Instead of kind of saying, here's what the whole node does, I can have an integrity proof specific to this virtual machine. That's good. And the other problem is that, well, now there might be multiple things running on my machine, right? This goes back to the software adversary. And so I want to basically have some sort of isolation property. Yeah, I want to say that if one VM is running, it can't kind of go and peek into the other VM and learn information about that. And kind of the way that is done, so this is kind of done essentially through the same type of technology, but maybe virtualized, this TPM. And this other part is done essentially by having a trusted memory manager and through encryption. Okay, maybe the somewhat surprising case here is that we all think, oh, we're just encrypting this thing, right? We're just encrypting the VMs. But if you think about it, somewhere somebody has to decrypt these VMs, right? And so they have to have the key. So really what you're saying is that there is a trusted memory manager, right? That's basically saying now we're running this VM, and so I'm not going to let it look at that part. And now we're running that VM. I mean, it kind of has the keys to everything, right? So really what we're trusting here is the isolation of that the code of the memory manager is providing. So basically we're trusting the memory manager. And the really important part here is, again, this is kind of this security versus friction trade-off. The reason why, you want to get a very low friction, so you want to make this work with very small overheads, single-digit overheads relative to a regular VM. And because of that, there were kind of design choices that made it essentially secure against, or the goal was to be secure against software attacks. And so in particular, what do we assume here? We assume that there's an adversary, and it can really kind of control everything, all the software running in the system. So for example, you might have a compromised BIOS, you might have a compromised hypervisor, you might have a compromised operating system, you might have compromised virtual machines, and still if your VM is kind of running as a TE, you want to say that this adversary that can compromise all those things cannot kind of look into you, and so you can still provide this integrity and confidentiality properties. Okay, so in particular, there are certain firmware components, for example, this memory manager, that we assume this adversary cannot compromise. Okay, so if I had to kind of strictly say, is it a software adversary? Yes, it's a software adversary, but there's pieces of firmware, software, I don't know how you want to call it, that the adversary cannot break into. So these are kind of the two properties that we can get from these things. So the first is kind of the integrity property. So this is the ability of attestation. And there's basically three things that you need to assume or trust in order to make this work, right? So the first thing you want to kind of make sure is that as we talked earlier, that there is a way for me to measure the code running on the VM in a trusted manner. So for example, if I measure the VM, but someone is switching what it's running there, that's kind of a man in the middle. That's surprising me. So then I lose kind of the guarantee. The other thing that I want to kind of trust is that there is this component that has a secret, and it can sign this measurement. And then the problem is that, okay, this signature, is some public key of somebody. How do I know this public key makes sense? There's basically a chain of certificates that goes all the way to some top-level certificate. So, each hardware vendor has their own separate root chain of trust, and you kind of have to trust this chain of certificates, right? So for example, if you're doing an attestation and you're using a Intel hardware, then at the end of the day, there is kind of a root Intel certificate that you have to trust is the correct public key. Okay. So anyway, so if you do trust these three components, then what you get is basically a integrity proof, right, or a validity proof, or if you want to call it a ZK proof, and all power to you. And the nice thing here is that it's publicly verifiable. Basically, what you have is a measurement of the code that is signed, and you have kind of a chain of certificates all the way up to some top certificate that everybody trusts. Okay, so it doesn't look like your standard validity proof, right? Your JAWS, but you can but for all intents and purposes, this is basically proving validity of. Integrity of this. I mean, saying that this is what is running on this VM. That's the good news, I guess, about the attestation, and isolation is kind of the other side of that, right? We want to kind of protect ourselves. Again, roughly speaking, this is a little bit of a caricature, but I think it's a reasonable mental model. is that there is this trusted memory manager. And this trusted memory manager, is basically letting different things run at different times. In particular, you can enter and exit your TE. Okay, so when you enter your TE, the TE starts running. And when you exit your TE, then other things run. Okay, and so that's kind of a very high level. You enter and exit it. And basically, when you are outside, when you exit it, then the memory manager takes care that if you try to read anything from that part of memory, then it's either blocked by the memory manager, or this happens to be encrypted. Okay, and when you're inside, then what does the memory manager guarantee? It guarantees that the only code that's running is the code that you put on when you attested to it. So you can't kind of put malicious code that will run on your thing. Okay, so those are basically the two things that are happening. And in terms of kind of what are you getting here, you're definitely getting some sort of something similar to FHE in the sense that you don't know what's being computed, but actually you get kind of something that's even stronger. You get kind of strong notions of obfuscation, right? I think even Elaine has this paper with Raphael trying to formally define some of these, what is the formal thing that you can get from confidentiality. But really think about it as kind of a strong notion of obfuscation in the sense that I can load code into this machine, and it's very hard for you to know what exactly is that code. Yeah, but there's a but here, right? So there, these are all the good things about confidentiality, but I guess there's definitely a lot of challenges. Some of the challenges you actually heard about in Elaine's talk related to side channels, related to memory access and storage access. But let's start from the top. I think what we've learned is that getting good confidentiality is actually quite challenging. Because you kind of want to get and with low friction, right? So if you want to have high friction, then it's less challenging. So the first thing really that you should remember, this is only good for a software adversary. If somebody has physical access to this machine, I think a lot of current TEs are very weak. Okay? You don't need any fancy attacker. And then kind of, there was many years of these horrible side channel attacks. Some of them were what's called micro-architectural, in the sense that the architecture was correct, the memory manager did the right thing, but the way the code that was written for these memory managers were implemented at the low level, right? So this is the micro-architecture level, was kind of incorrect. Wasn't following the requirements of the architecture. And so that's where you had these horrible bugs at the micro-architectural level. And obviously there were other problems. So over the years there were many problems, and I think many of them are fixed. And I think my understanding is that it's getting much better. So there's less of these things over time. So that's kind of the side channel side of things. There's the memory side and the storage sides. I kind of mentioned this oblivious computation. So basically there's kind of two paradigms of using these TEs, and this is kind of what we'll cover. So the first one is kind of defense in depth, and here I urge you, or I want to say basically, even if I'm not going to urge you, the world is just going to force you to default to use TEs. The reason is kind of the costs will be marginally very small, so few percentages, and it'll basically be like you're running, network with HTTP and not HTTPS. Maybe 10 years or 15 years ago made sense. Today people will look at you as if you're a bit weird. Like, why aren't you just doing this simple addition of security? So I think in the future, you won't have VMs that are not running inside these types of things. Anyway, that's kind of the view here, and I'll kind of talk about cases where it actually makes sense and it actually provides you with meaningful advantages. And the other is kind of saying, no, I really, like, my application really depends on the security of these TEs. This is fundamental to the security that I get. And really, what does that imply? So what are we kind of, when we do that, what are we saying? Well, we're kind of saying that we trust that the cloud service provider that's running these TEs has physical security, and they will kind of not allow certain types of adversaries from getting physical access. I do not know whether maybe some organizations can have physical security to these CSPs, right? So this is the assumption that you need to make. And obviously you also need to make this assumption that you're trusting the hardware providers to actually implement this thing correctly. And even if you kind of trust those two components, right? So you're trusting the CSP for physical security, you're trusting the hardware providers to actually implement all these things correctly, fix all the bugs and all that. then you still have to kind of make sure that the way you design your application makes sense and doesn't leak things through kind of non-oblivious computation, for example. Okay, so these are the two things, and here's kind of a short list of interesting ways where TEs can help in the space that you guys are more interested in. So obviously, wallets and bridges definitely use secure hardware. If you want to kind of get better anonymity and privacy when a wallet is reading, you can get that. Integrity proofs, which we'll talk about, block production and protection from MEV. Consensus protocols, which is kind of what I'll be talking about next. So don't worry, we'll hear a little bit about consensus. Obviously, if you want to run in private contracts, then this gives you kind of a very nice thing to do. And I'll also talk about confidential inference. So these are kind of a few things that I'll mention. But really, what I want to focus on is consensus. And I want to start with kind of a thing that you've probably heard. So for some of you, this is like really well-known and boring, and for some of you, maybe this is like very new. But you've probably heard this thing that you can't do consensus better than 33% against Byzantine adversaries. Maybe you've heard that for Ethereum say that, or if you've heard that in the blockchain space, then you can ask yourself, well, why? Why can't I do that? What's the fundamental reason why this is blocking me? And I think this is kind of really an amazing property of theoretical computer science, that the lower bound is actually like this very, very simple 3-node case. There's just 3 nodes, and you prove some impossibility, and that basically implies like these lower bounds for why if you have thousands of validators, you can't do better than get like 33% for them. So this is really nice, and if you know this is what's called this split brain lower bound. Okay, so what is the problem we're trying to do? We have 3 nodes. And what we're trying to do is reach consensus. So we're trying to reach consensus on either 0 or 1. That's kind of what we're trying to do. Okay, and there's 3 parties, A, B, and C. And A and B are kind of going to be, reasonably good parties, and B is going to be our Byzantine party, the malicious party. And the goal of this malicious party is basically to make people disagree on the outcome. Right? They want one party to think the world is 1, and one party to think the world is 0. And the way this lower bound works is very, very simple. This B adversary basically splits its brain into 2 parts, into a left part and a right part. And the left part, it basically talks with party A and says, hey, my input is 1. And in the right part of B, it says, hey, my input is 0, and talks to C. And because of kind of network delays, then kind of this link actually never gets any message across. So basically what happens is that B talks to A and says, hey, I have a 1. And B and A all look very, very honest, right? And basically what they think is that C crashed. Right? So from B and A's perspective, it just looks like C crashed. And it's the opposite. If you think about B and C, then from B and C's perspective, they have both input of 0, and they kind of think that A is crashed. And so it turns out that if you kind of do this split brain, then basically A will say, okay, so let's decide on 1, because we just have 2 inputs of 1, there's nothing else to do. We have to be valid, so we output 1. And then kind of C says, well, B is saying 1, 0, and I have 0. And so, the only thing that we can output here to be valid is 0. Okay, so this is kind of the classic lower bound. If somebody, hasn't seen this before, and if you have a question, then please ask, and I'll kind of give you a little bit more. Or it makes sense. Make sense? Good, great. So yeah, so this is basically this split brain attack. And I guess the observation here that I want to make is that we actually don't really need to assume the adversary is Byzantine, right? Remember, what is the Byzantine adversary? Well, it actually steals the keys, and it can do whatever it wants, and it can run a different protocol. It can kind of wreak havoc. But actually, it's doing something much simpler. I claim that the only thing it's doing is rebooting the machine. Just rebooting the machine once. Okay, so basically, what's the attack of this reboot adversary or rollback adversary? Well, it boots up with input 0, and then it just talks to C. Okay, it talks to C, and C and B talk, and they don't hear from A, so eventually they just decide on 0. Everything else is kind of delayed. And after B kind of makes sure that C decides 0, then B is really happy, because what it does is it just reboots the machine. Okay, so it's malicious in the sense that it rebooted itself. And then what it does, well, it changes its input to 1, right? So it kind of chooses a new input, and then kind of does the same thing with A. So I guess kind of the main point I want to make here is that this very simple lower bound. First of all, this kind of explains to you why all the BFT protocols that in the blockchain space that work for partial synchrony with the Byzantine adversary cannot do better than a third. But on the other hand, it actually shows you that the adversary can be very, very weak. Okay, makes sense? Good. So yeah, the only thing we needed to do, essentially, is to keep our identity the same over reboots, right? Because if, let's say I reboot, and then when I reboot, I talk to A, now A is like, oh, you're a different person because you rebooted, then this proof wouldn't work. Okay, so really kind of what I needed here is to say that when I reboot, I still maintain my identity. Okay, so what does that have to do with TEs?
Counter?
Sorry?
The counter?
Monotonic counter.
Counter. No. That's
Increment
close.
the counter every time you reboot or no? You
Oh
can't?
yeah, oh, yeah. If you had a counter, that would be nice. Yeah, yeah. Yeah, if you had a reboot counter that you could trust, then you could basically change it, then your identity would change. Yes, exactly. The problem is that you don't have I mean, we don't know about, at least these TEs don't have a counter, right? Okay. But yeah, I think that's exactly the point. The point is that, and we'll show this in the next slide, like basically even if you believe that you're running in a TE and the adversary can't do a lot, if the only thing the adversary can do is let you run and then reboot you and let you run again, you're in trouble. Okay. So yeah, here's the good thing. So here's what you do, right? Basically, here's how you run consensus with TEs. What you make sure is that you build your private key inside the TE, right? Why is that good? Well, because when you build the key inside the TE, nobody can see it, right? It's confidential. Nobody gave it to you, right? It's a new, fresh key, so you can be very, very secure about it. And then, just like we assume that we have some PKI, there needs to be some mechanism that your public key gets kind of recorded everywhere. So there's like some sort of root of trust or some sort of Genesis file that contains all these public keys. Okay, so this is this PKI assumption. And with this thing, basically, what you get is for TEs that if you have a Byzantine software adversary, right, so it can do whatever it wants, but it doesnn't have physical access, because if it had physical access, it could break your TE. It is essentially equivalent to this oblivious omission adversary. Basically what I'll say about this, if you know, then great. If not, then I'll say, what is an omission adversary? Basically, the only thing it can do is kind of block messages, right? So if you send a message, it can block it, but it can't kind of change the message, or it can't see it can't see your secrets. And really, the high-level intuition here is that what you get is non-equivocation. So if I'm running inside a TE and my code says I'm sending, for round one, message that contains the value A, then no matter what you do, right? If you are basically all you can do is like block this message. You can't cause me to say A and B for round one. This is kind of this fundamental property of non-equivocation. You cannot say two different things in the same round. And once you have that, then you can kind of implement consensus with 2t plus 1. Right? So you can do this 2t plus 1. You can do this even for a mobile adversary because it's oblivious. I didn't even say what that means. But again, roughly speaking, you kind of don't see the internals of the code. And you can do this with n-square communication, which kind of is the best you want. And you can do this even if you don't have a DKG. And you can do this even in asynchrony. So all the wonderful things that you want, you can get here with consensus. Okay?
But you're not claiming that a TE can do that, right? Or are you claiming that?
Yes. So I'm saying if you have a TE, and it does this thing, it chooses its private key, and it broadcasts this private, so you have a Genesis file with this thing, then if you assume a Byzantine software adversary, you can get 2t plus 1. Mm-hmm.
So I'm trying to understand why you get oblivious omission adversary.
Okay.
Why could I not restart it to the beginning of the round? Let's say, I have so many rounds of messages, I replay it.
Okay, so you're
But I emit different subsets, let's say.
This is like the question of the next slide.
Okay.
So the next slide talks exactly about see, you kind of look at this and say, oh, this slide says the good, so probably what's going to be in the next slide is either the ugly or the, there's two choices, right? But you're right, like you're asking basically, what can we do if we reboot? Right? And that's basically what this next slide asks. So there's a great question. I don't know, there's all these different definitions. But anyway, so what do we do when a VM needs to reboot? So one option is basically say, well, I'll just use the same private key. Does that make sense?
No, then you're back to just Byzantine fault.
Then I'm back to the reboot adversary, right? So if I basically keep this key, store this key, seal it, and then when I reboot, I wake up, I use the key again, right? I'm basically allowing a reboot adversary. Okay, so that's not great. So that's what you cannot do. Okay, and that is kind of so everything until now was amazing because we basically said, well, we need 3f plus 1 in usual BFT, but here we can get 2f plus 1 because we're using T's. That's great. And so kind of what we need to do is create new private and public keys, and that basically means that it's a reconfiguration event, right? It's basically saying you're adding a new node to your system, and that's annoying, but that is kind of the world here. So again, as long as you have f+1 parties that are non-faulty, you can kind of use your own system to reconfigure your own system. You can record new members, and that's great. But if you kind of lose liveness, the system cannot make progress because too many people rebooted at once, then you kind of need something stronger than a PKI. You need to have some place where you need to record, what are these new public keys, and you need to trust this new place. And so I'll call this layer 1 trust anchor. Yeah, say that you can kind of deploy these on multiple different clouds to get better liveness for some things, not for all. And I would say, given this problem, that every crash, basically, or every reboot requires you to rekey and reconfigure, it kind of makes them not great for layer 1s, but actually makes them pretty natural for layer 2s, because you can use this layer 1 as your trust anchor. That's kind of, I guess, the main thing. And here's kind of, how it's being used. So I'm going to tell you very, very quickly about, this notion of confidential inference, which is, a new type of use case. All the large companies are kind of looking at this confidential AI space. And all of them basically use kind of this layer 2 state machine replication or consensus protocol that uses 2T+1 using TEs. And if you think about inference as a task, you can think about that task as basically like a payment channel. Your inference server is just kind of set up the channel. But once this channel is done, then when you're interacting with this inference server, that doesn't go on-chain. These are kind of interactions that are just between you and the inference thing. So that's why I'm going to call this a layer 2 application. Maybe this is the killer layer 3 application. So maybe this is kind of the killer layer 3 application. Here's one example of this. This is kind of the Microsoft confidential inference. This is Mark Rusinovich's blog post. And what you can see here is kind of the data path. An application is kind of asking and getting a confidential inference, and here you see a GPU. Everything here is attested and secure and so on. And over here on the top, you can see there's a key management service, an attestation service, and also a ledger here. Right? And this ledger is basically a 2T+1 consensus engine. I gave very long talks about the system. There's a lot of interesting things about it, and confidential inference itself is kind of a very interesting topic. But a very high-level thing I want to show you here is that this transparency ledger is key to it. Yes, please.
Why do you need consensus for this?
You need a place to record what are the most recent values that you trust to, for the inference server. So for example, what is the most recent software? What is the most recent models and so on? And so you kind of need to make sure that that I'm not giving you kind of an old buggy version in some sense. And then you need to make sure that this place has like high availability, because if that is kind of your single point of failure, if that place fails, you fail. So there's like 3 things you want to guarantee here. One is you want to get high availability. The other is you want to get safety, in the sense that you're really you're guaranteed that you have the most recent attestation that you're going to verify through. And the third thing that you want is confidentiality, right? So you also want to make sure that if you're making these queries, that thing is not being made public.
So in these applications, is the T into T+1 like 2, 3, 4 in that range, or are we thinking of larger numbers?
I think for now they're small, yeah.
Wait, so are you saying this is running a 2T+1 partially synchronous consensus protocol using TE?
Yes.
Is that necessary, or?
I don't know. Necessary is a mathematical notion. This is, I'm showing you like a system and giving you kind of an example of one example of a system. Here's another one. This is Google. This is actually not inference. This is kind of confidential federated analytics. But again, I won't go into the use case too much. I'll just say here again. You look here. There's something called a T-hosted ledger plus Keystone. Well, just as Elaine said, this is running a 2T+1 partial synchrony consensus protocol. Okay, this is another example of where I guess confidential AI use cases are kind of using this type of paradigm. Here's the third one. This is Apple Private Cloud Compute. Again, they actually are using something a little bit different. This is what's called a transparency log, but again, morally speaking, it's very similar. And there's this system has a lot of interesting aspects that I won't go into. But again, the goal here is to kind of extend the inference from your phone to the Apple cloud. And you again want to kind of use a ledger to guarantee that you're actually talking to the most recent and most secure version of this Apple cloud. And here is, finally, WhatsApp also have a blog post, and there they also have a ledger, which is also using a partial synchrony protocol that is 2T+1.
think these are the kind of applications where traditionally you kind of argue Byzantine faults are overkill anyways, because it's just kind of an internally run kind of permission consensus protocol, right? So like, why?
Yeah, so I would say all of these systems basically, or I would say confidential inference. The thing that changed here is that many of these queries are so intimate that you really want to get a very high security where you do not trust your CSP. So kind of if I had to say what is different or why people now want, a Byzantine fault tolerance, is because the intimacy of these queries are such that you actually care about an even worse adversary. Now, to be honest, right, it's not that all your inferences today, right, when you go to ChatGPT, go through this. This is like an experimental system. So I don't know if this is going to hit product market fit or not, right? But this is kind of, some people are betting that the end game for inference will be confidential inference. Okay, so this, I think it's an open hypothesis in that sense at this point.
What are they doing to obtain privacy? Like you put inference inside TEE?
Yeah, this thing see this thing says it's running in a TE, and this thing says that there's actually an attestation of the GPU. So this whole thing is running on a TE. Yes.
I assume it needs many GPUs, like multi-GPU.
Yeah, there's many challenges. Yeah, I have a long talk only about this, but not. Yeah, I apologize. Sorry. I apologize. There's like another 2 topics that I really want to talk about. So, and I don't have enough time, so I'm gonna rush. And if you want, I'll do follow-up questions on confidential, which is like a very cool topic, and I've been working on it, so I have a lot to say about it. Okay, so yeah, TEs and integrity. Sorry, so we started with consensus, and then I kind of gave you here's an example of people that are using it, and now I want to go and talk about integrity, and kind of again make this observation or this analogy between I guess integrity and liveness and confidentiality and safety, in the following sense that if you have like n things and one of them fail in safety, that's bad, because even one failure in safety is not good for you. And similarly, if you have n things for privacy and one of them kind of leak information, that's not good for you, right? So kind of safety and confidentiality is really like an n out of n thing. While if you look at liveness and integrity, you really like one of these things to succeed, and you kind of make progress, right? So if one of them kind of make progress, then you have liveness, or if you want to prove integrity, at least if somebody is saying you have integrity, then that's already kind of a good signal. Okay, then we're actually going to take advantage of the fact that in some philosophical sense, these properties are weaker than this sense, in order to kind of look at this notion of using 1 out of 2 or 2 out of 3 type of solution. And here's some challenges with zero knowledge proofs, or I prefer to call them validity proofs. And I would say they mirror the problem that happens with TEs, which is that typically, when you're trying to prove very, very large circuits, your trusted compute base is not just the prover itself, but it's actually that this huge circuit doesn't have any bug. And that's actually very hard, and and there will be bugs, and you will need to update it and upgrade it. And I guess in many of these systems that are using it, there's kind of this idea of having a security council. And so what ends up happening is that you want to have a permissionless and trustless system where you only trust cryptography, but at the end of the day, you're trusting a multi-signature. Maybe 3 out of 5 or whatever, some multi-signature that can basically override your whole cryptography. Okay, and so kind of I guess one kind of major goal for these proving systems is to improve that and rely less on a security council. Here's kind of a very nice idea, which is basically let's compose integrity of 1 out of 2. So how we're going to do that? We're going to do that by saying, well, we're going to take every statement and run it through 2 different provers. So one prover is just going to give us a zero knowledge proof, the good old, the trusted, wonderful thing, and the other is basically going to give us a signature of an attestation that goes up all the way up to the root of some hardware provider. Okay, so these are basically 2 different types of proofs. They're both validity proofs, and the idea being is that if there's a bug in one or in the other, then the other one will hopefully catch it, or the probability of having an error in both of them is small. Okay, that's the idea. Okay, so what would you concretely do? Well, if both of them say yes, then that's basically committed, right? That's kind of your execution. And if one of them says no, then you can kind of go and do more fancy things. So for example, one of the options is to say, well, if you don't have, if only one of them, if both of them say no, then you just say, okay, abort. But if one says no, one says yes, then maybe you can say, well, now I'll give you like a week for doing fraud proofs. That's like a third way of doing integrity checks. So that might be kind of a fallback. Or you could say, well, if one says yes and one says no, we'll let the security council decide. Or we can let the security council decide after 3 days, right? So there's a fraud proof, and you can do all these kinds of mixes. But I guess the high-level idea here is really that if you're worried about, or if you want to get high quality, high security, zero knowledge proofs, then this approach of defense in depth doesn't add a lot of costs, right? The friction is small, and the additional security is that it allows you to deal with some of the potential bugs that you might get. That's kind of a way of getting defense in depth. So that's kind of the idea here. And again, I would say this is again a security versus friction trade-off, right? So I think many systems today maybe just prefer to kind of say, yeah, we'll just we'll use our prover and we'll have a council. And so that's kind of the lowest friction approach. And adding kind of these systems adds some friction, but really what I want to argue here is that the security value is good enough that you should look at this trade-off and say, hey, this actually makes sense. And this should be kind of in some sense the default, going back to using default, using TEs as a default. Great. So that's kind of one thing. Oh yeah, okay. There's the end game. I won't talk about it too much. How will we do this in the end? And if you do have a security council, then please use TEs for the security council as well. That's another thing, but let's ignore that. Yeah, and I want to kind of go very quickly into my last topic because this is like a very fun topic. Yeah, and so is threshold cryptography broken? Yeah, okay, it's not broken in terms of the theory, right? But what's the problem with having councils? And I guess the real question is like, why isn't there traction? Why aren't we seeing some start of product market fit for MPC? And that's kind of the question I'm asking here. And really, like for example, when I ask Vitalik, then his answer is that parties can collude, and there's no way for you to kind of figure out if parties collude secretly and kind of leak these secrets. So in a sense, the problem is not the cryptography; it's the crypto economics. Okay, and the problem is that basically, if we're doing threshold cryptography, let's say 2/3 of us are holding a secret and we have to agree on something, then we can also secretly meet and collude and kind of leak this secret and gain some things and make it such that it's very hard to detect us and all these problems. And therefore, I guess, in that sense, threshold cryptography is broken, or you're not seeing a lot of use for MPC that is based on threshold. Okay, so kind of the punchline here is that why doesn't this happen on blockchains? Well, we have this notion of accountability, where basically, if many people are trying to collude and break the consensus, then we have these beautiful results. Some of them are, people here in the audience that show that basically a lot of people are being detected and can be cryptoeconomically punished. Right? So accountability is kind of the reason. The cryptography or the distributed computing says, yes, you have a third, but the reason like this third doesn't collude to become a half, more than a third, is kind of because of these cryptoeconomic things. And I want to say this has also been extended to liveness. So so you say, okay, this is why blockchains are safe, but why are they live, right? So they're live because they're incentivized to be live. And again, there's like a new exciting work about accountable liveness. And I think these are things that are very important. And the thing I want to talk about here is accountable privacy, and really want to say, well, how can we get the analogs of accountable safety and liveness that we get in kind of blockchain systems to MPC or threshold cryptography and so on? And the big problem here is that if a human has keys, then kind of an adversary with a wrench can kind of convince you that it's actually quite nice to collude, and then you would collude, right? And it's completely secret. There's no way you can collude without anybody seeing it. So there's no way for you to be accountable. So one solution that is kind of obvious and nice, I think, is that even though a human might be the one that's putting the stake, right? They're kind of the validator of this MPC node. It actually doesn't control the secrets of this node. So the secret itself is held inside a TE. Okay, so even though I put money into it, I'm the staker, I actually don't have the secret to collude. This secret is going inside the TE. What is the problem? Well, the problem is still, some sort of physical security, right? So the problem is that this is great for an adversary that can control the network or the software, but not if the adversary can actually kind of physically go and take your key out of your MPC server. And so for that, basically what you want is your MPC server to actually be able to look at the environment, sense the environment, right? You're all laughing now, but let's talk 5 or 10 years from now, and basically understand, right? So essentially through kind of AI tools and robotic ability. Robotic might be just a simple camera. If there's anybody near me, right? If there's anybody, one option is just send it to a satellite, right? Then it's far away. But it can be physically near us, but kind of protected. And if it detects something bad, what will it do? Not only destroy the secret, but we want to make it accountable. It'll actually publish a slashing effect that will kill your stake. Okay, so it's not just kill itself, but it will actually harm you. It will punish you.
Who's you?
The staker, whoever put the stake to run this thing. So there's somebody that has that's running the system, but he doesn't. That person does not control the actual.
You're saying the person who was responsible for physical security and failed in that duty will be staked and will be slashed in effect.
Yes, or I would say if you want to stake this system, then you need to guarantee that nobody's going to attack it. That is your guarantee, and that's your accountable privacy in some sense. Yeah, exactly. Okay, one more minute. I think So this is the slide. TEs plus robotic AI will give you MPC in the real world. And so I think publicly verifiable secure hardware is very interesting. I won't talk about fairness. There's wonderful things about fairness. TEs as a security anchor, that's kind of one type of use case. The other is defense in depth. And here's kind of a list of nice things that I think are the future of trusted execution environments. Publicly verifiable hardware, accountable privacy. We can talk about integrity and FHE. We didn't. Confidential AI, which we did, and I'm happy to follow up on. And eventually, you think it's kind of a joke, but eventually we'll get to kind of robots and physical security through robotic interfaces. Thank you. Thank you very much.
Even in that a robotics world, there's still cryptography questions to solve. I saw something. Who says if this was a human being or not? What if someone tries to send something that looks like a human being but not a human? Do you see what I mean? It's it becomes a computer vision question at this point.
Yeah, that's why I have a robotics and AI.
And I see. Okay,
yeah,
sure. Yeah, I don't know. Sure. Yeah.
Okay. I mean, you need to have some long-term hope, right?
Of course.
Okay.
So I guess I have several questions. One is you mentioned your vision is everything should be TE. So let's just take Amazon for example. They have Nitro Enclave. What's preventing them just from offering TDX container? I mean, shouldn't that be much more secure than Nitro Enclave? What's the barrier in practice?
I think that in practice, what will happen is that the friction of running a secure enclave like Nitro or like TDX will be so low, it will be like the friction of running HTTPS versus HTTP. There is an additional overhead, but it will be so low that it will become the default.
Yeah, I agree with that, but I'm just asking why isn't this happening? I still cannot get the TDX enclave on Amazon.
Yeah.
There's nothing SGX. There's only Nitro. This has been the state for a long time.
I see. So it's hard to make predictions about the future, So it's just it took an inflection point for people to use HTTP to move from HTTP to HTTPS. Some people say it's actually because of hardware changes that enabled to do this efficiently. Some people think it's because of the Snowden revelation. So I don't know what will be kind of the tipping point. I do think that from my understanding of what's happening in clouds, that definitely in the next few years, the enablement will be much, much better.
And then back to the TDX, you said you are going to talk about TDX. So how do you compare TDX's trust model with SGX? And what is, and maybe your take and not necessarily Intel's take on this?
That's a really good question, but it's not this call. I would say that since I didn't talk about SGX, then let's take this offline. Yeah, but I have a whole large.
I thought there was
answer.
One part of your talk you were referring to.
Yeah,
SGX.
but I didn't actually talk about SGX, so I don't want to just that. Then that would be
But that part about general computation that you were not referring to SGX.
No, but I have a lot to say about that. So let's take that offline.
Okay, so that part was referring to TDX.
Okay. Yeah. Let's take that offline. I think I have a lot to say about that.
Is there a formal model for physical security? Maybe I have a circuit and I cannot extract information from that circuit, no matter if I rewire things or something. Is there
No, I think that's a really good question, and I can imagine a whole area there. I don't know of it. I'm not aware of it, but I think it's a really good. I think we have very coarse notions. Even if you saw my definitions, they were very vague, right? They weren't very mathematical. So I think that's a really good question.
So capability for measure, is that only a TPM thing, or is it still TE also? Does TE also need that?
Yeah, TEs also need that because you want to do attestations. So anytime you attest, basically what you're saying is that the code that's running.
I thought that's measuring inside, right? That's code running inside TE.
So when you say inside, I mean there are different parts of the hardware, I would say. So I want to separate the software, the firmware that is doing this, and the physical interface that's actually looking at the bits. So I would say you need some sort of physical trust in addition to the software trust that you're making. And I'm incorrect in the sense that in some systems, this is all virtualized. And so in those systems, it's really you're trusting. Unfortunately, you're trusting a lot of software. If that would be kind of one of the challenges of, say, these hypervisor-based solutions, right? That there's a large software that you're trusting.
But if you use hashes, Merkle trees for everything, for the entire external memory, then it's again measuring something you have control over instead of measuring something you.
Yes. Right? So that goes back to the friction of kind of building a Merkle tree on everything and verifying it, and then when you read and write. So there's always this friction, security friction trade-off. And I guess a lot of these systems were built to provide very low friction and still give you some meaningful security. And you're absolutely right that if you want like a high security application, like the examples that Elaine talked about, right? You need oblivious computation, and you want to make sure that when you're reading something, it's verifiable and so on. It's very important.
You mentioned that we have the integrity and privacy assumptions under software adversary. Does the integrity assumption underline the liveness assumption?
What do you mean underline? Like
is it implied?
Yeah. I mean, okay, yeah, of course. So basically, yes, that's a great observation. I mean, in part, what we're assuming that we can do this, but like the system won't get stuck doing it. Yeah. So that's a really good point. Yeah. So there's like, so we're implying that this, the underlying kind of firmware that's doing it doesn't have bugs that, for example, have liveness bugs or safety bugs. Yeah, that's a really good point.
Yeah. So like the software adversary can't tamper with liveness.
Denial of service. Yeah. So that's a really good point. Yeah. So one thing you can, like two different types of attacks are, one is kind of to, destroy this trusted software. The other is just to do a denial of service on it. And so that's a really good point. Yeah. So you have to guarantee both of these things. And again, I would say, the best of my understanding, at least for software adversaries, the hope is that this is the case. But for physical, I'm not sure that's the case.
Well, the wrench is still there. Right?
Yeah. No, you have like these more refined things. Oh yeah, you can use a wrench.
Yeah.
No, but for example, like the sysadmin, if you use a wrench against a sysadmin, that doesn't help you break a T.
No,
right?
you use a wrench against the T itself.
Oh yeah, okay. Yeah, that breaks liveness. Yes, of course. I forgot about that one. Yeah, thank you.
Thanks again.
Thank you.